I still love music, and that was my first career. And this commercial helped to get this car in this successful place after the old Beetle. So I was thinking, so how can I make the connection to this talk I'm giving now? And here is one. A few years after that VW commercial went around the globe, I had to make a decision. The decision was about, should I continue on the stage being an entertainment musician, or should I try an academic career? Staying on the stage was for me the safe option, and I would have made much more money than a poor assistant professor. Going into academia was the unknown, the uncertain option, because I could never know whether I will make it into a professorship. And so I took the uncertain option. And I didn't make any calculations, but I thought, you should take the challenge. And I would regret it if I wouldn't have taken it. So that's the reason why I'm here, and not sitting here as a musician. Okay, so my topic is decision making. How should we make decisions? How do we make decisions? If you open a textbook in economics or in behavioral economics or in philosophy, you will likely read the following thing. Good decisions follow the laws of logic, the calculus of probability, the maximization of expected utility. And if you don't do that, then your behavior ends up in a chapter on cognitive illusions. Logic and utility theory are beautiful mathematical theories, but they don't describe how most of us actually make decisions, including those who write these books about decision making, as the following story illustrates. A professor from Columbia University in New York had an offer from a rival university. It was Harvard. And he couldn't make up his mind. Should he stay? Should he leave? Should he accept? Should he reject? A colleague took him aside and said, "What's your problem? Maximize your expected utility. That's what you write in your books all the time." Exasperated, the professor responded, "Come on, this is serious." I would like to invite you today into a voyage into our research on decision-making under uncertainty at the Max Planck Institute. I will first start with an important distinction that is as often being ignored between risk and uncertainty. Then argue that the tools for uncertainty are by definition not logic and not probability theory, but heuristics. Then I give you examples about how heuristics work, and I will explain a very beautiful feature that heuristics have. So they have less effort, but they can at the same time be better and more accurate than more complex strategies, including big data. So the key message is, the farther you are in a situation under uncertainty, make things simple. And if things don't work, don't make them more complex, make them more simple. Okay? That's the program. Are you ready? Then let's begin. Here's the key distinction. Risk is a situation where you know all the future states of the world, all the consequences, and all the probabilities and utilities. So if this evening you play the roulette in a casino, you are in a situation of risk. All future states, that's all the numbers from 1 to 36 plus green, all the consequences, and the probabilities are known, and you can make the calculation and find out that in the long run you will lose. This is also the world of neoclassical economics. It's the theories, the key theories from Arrow to Debreu, or in finance, Merton Markowitz. When Harry Markowitz, who got his economics Nobel Prize for solving a problem, namely how to invest your money in N assets, when he invested his own money for the time of his retirement, he used his Nobel Prize winning optimization method. So we might think, no, he did not. He used a simple heuristic, 1 over n, which means divide your money equally. So if you have two options, 50-50, 3 a third, a third. Studies have shown that this simple heuristics can make more money than the method for which he got the Nobel Prize. Why? Because in the real world of finance, we are not in a world of risk. We are in a world of high uncertainty. And the key point is, the same methods that give us optimal solutions in a world of risk may not at all function in a world of uncertainty. That's what I want you to understand. And I will talk about one tool that is helpful under uncertainty, and that's called heuristics. And heuristics are fit for a world where you need a robust solution because there is no optimal solution by definition. Okay, let me explain what a heuristic is, using an example from sports. Who of you plays baseball? One. Cricket? 5. Football? A few. What do you do all the time? So imagine a ball is coming in high, and an experienced player knows immediately where he or she should run in order to catch or stop the ball. How does the player do that? What is the mechanism? And here are two theories. One is, it's a complex problem, therefore, the player needs to do something very complex in his mind. That's the typical theory. That's also the theory that underlies many big data applications. It's a complex problem. We need lots of data. The other view is, it is a problem under high uncertainty. Therefore, we need to make it simple. So we should look whether the player actually does something quite simple. Let me start with the first vision. So, the complex theory. Here's a quote from Richard Dawkins' famous book where he explains how a player catches a ball. And basically he says that the player behaves as if he would calculate the trajectory by solving a few differential equations and then run where the ball is coming down. He knows, he puts in the as if, that's eco terminology. He knows it's not true, but what else could it be? Something similar is going on. Yeah? Experiments with players, with experienced players, show that nothing similar is going on, but something totally different. And the outfielders use a bunch of simple heuristics to solve the problem. And I'll show you the simplest one, which is when the ball is already high up. Before I show this, let's go in the complex solution. So has any one of you calculated trajectories of balls? That's how it goes. And it's important to notice the problem is not calculation, We can calculate almost anything today. The problem is estimation. So the alpha is the original angle from which the ball was shot or kicked. And you have to estimate that. And that's the key problem that we have. So, and those of you who regularly calculate trajectories will have noticed that I left out a few variables, like spin and the wind and so on. But that's the point. What else could an experienced player do? Experiments shown that they use heuristics. Here's a simple one that works when the ball is already high up. And it has 3 steps. The first one is fixate the ball with your eyes. Second, start running, and then run in a speed and change your speed so that the angle of gaze always remains constant. This player is doing that. Observe that the player is running in a way that the angle of gaze is always constant. And what happens then? He's exactly there where the ball is coming down without calculating that. Do you want to see it again? The very point is the player can ignore all the variables, including the calculations, in the formula that you just saw, and also the variables that are left out, and needs to focus only on one single variable. That's the angle of gaze. And the problem is solved. This is a heuristic. A heuristic is a useful method to solve a problem, and at the same time, with a minimum of information and computation. In that case, a single variable. If you have a dog at home and throw a frisbee, you will observe that your dog is not trying to calculate the angle of the, the trajectory of the frisbee, but will try to run in a way to keep the optical angle always constant. That's the thing. So, this is an example of a heuristic that's used unconsciously. Most of the players don't know what they're doing, but they can do it. That's called intuition. Intuition is defined as a behavior that's based on many, many years of experience, and the person with the intuition knows what to do, but doesn't know how to explain it. That's the point. Part of our research is to extract heuristics that are unconscious and model them from the experts and then teach them consciously so that you can quickly learn that. So every heuristic that we have studied can be used consciously and unconsciously. So the idea there would be an association between heuristics and unconscious is not empirically correct. So here's an example. You may remember the miracle from the Hudson River. A plane took off in LaGuardia Airport, and a few minutes later, something totally unexpected happened. A flock of Canadian geese collided with the plane. And the engines of modern jets are designed so that they can digest birds, but not Canadian geese. They are too fat. And the improbable event was that they flew in both engines, which then shut down. We know from the passenger reports that they noticed that it became silent in the plane. We also know that there was no panic, but prayer. The 2 pilots, Sullenberger and Scalz, immediately turned around in order to see whether they can make it back to one of the airports. How did they make this decision about life and death? Did they calculate a trajectory of the sailing plane? No. They used the same heuristic, now consciously. In that case, where your plane is sailing, that works like that. Here is the cockpit window shield, and you fixate, say, the tower of the airport, and if the tower is going up in your windshield, you're not making it, you will hit in before. That can be done in a few seconds, and it's more reliable and safe than if you do this with an algorithm who can run on the wrong assumptions. So that's an illustration of a heuristic And the point is, heuristics can be fast, work with little information, and nevertheless can be excellent. The intuitive use of heuristics and intuition in general is something that has in our society something is suspicious. And behavioral economists have worked lots to run experiment after experiment to show that your intuitions are unreliable. They are sometimes, but also calculations are sometimes unreliable. It's nothing per se. I give you an example from the big corporations I've worked with. These are international corporations. And I have asked the leaders up to the highest executive how often they base a decision, an important professional decisions they make, or the group that's making, at the end at a gut feeling. And I emphasize the end because, of course, they look through the data and more data, but then the data doesn't always tell you. And if an executive then uses his or her experience and feels you shouldn't do that, and goes with this, that's what I mean. Clear? So I'll show you just one of these companies. It's an international technology provider. And the question was, how often is an important decision at the end a gut decision? What do you think? 0%? 1%? 2%? 5%? More? 0%?
Really high.
Pretty high? Oh, yeah, you have to talk with one another. Okay. Here it is. So what you see is there's nobody who says, no, I don't. Okay. I'm sorry, the slide isn't there. Now imagine a slide, which says, which shows you that in the middle, at 50%, is almost everything. That's what they do. But these same executives would never admit this in public. And I've seen several ways to get around of this. One is defensive decision-making. Defensive decision-making means, so I believe that option A is the best for the company, but if something goes wrong, it's my responsibility, and if it's gut feeling, I by definition cannot explain it. Therefore, I rather recommend a second best or third best option B, which is not so good for the company, but better for me. So defensive decision-making means that you protect yourself and hurt your own company. And what you see here is just one example, a typical one, where I asked them, think about your last 10 important decisions where you were part. How often were they defensive? And there are some people who say, never. If you talk to them, you get answers like, if the company is in good shape, I'm in good shape. If it's not, I'm not in good shape. So the identification between this executive and the company has worked. On the other side, you see people who say basically always, I protect myself and recommend second best decisions. And these are in the tendency rather in the lower level. On average, every second, every third decision is defensive. This is typical for large corporation. And you can just make a calculation how much money they are losing and also how much fun they are losing if you always have to be defensive and protect yourself. So that's the, what is the message of that? Yeah? So if you are defensive, you are not, your chance to really go after innovations, because you need courage for innovations, is low. Here's a recipe about how to stop or slow down innovations. Always mistrust gut feelings. Ask for a justification for each new idea. and promote a negative error culture, defensive decision making, and lots of documentation and more documentation. This is a disease that we have across the Western world. It's increasing. For instance, if you visit your doctor and ask your doctor about a condition, and you believe that your doctor tells you the best thing for you, you may be lucky and have a good doctor, but many doctors practice defensive medicine. They will not tell you the best thing for you, but something that protects the doctor from you as a potential plaintiff. That's a situation that's particularly prominent in the US because of the US tort law, and there are too many lawyers in the US. And in one study, over 800 American doctors were asked whether they practice defensive decision-making. What do you think? What proportion of them said, yes, that's what I have to do? 93% in this study. And that's probably an underestimate, because not everyone admits it to the other, to him or herself. Like that here is also probably an underestimate that you have seen. So, now I'll give you one example about the power of another simple variable. We had one, gaze, yeah? But that doesn't help you necessarily in business decisions. And I'll pick a problem. So assume you have a company and you have 100,000 of customers, and you want to send targeted information, catalogs, or anything else, and you don't want to waste your materials on people who won't buy anymore. So inactive customers versus active customers. How do you predict who of your customers will be active and who not? It's a very difficult problem, and it's a problem clearly under uncertainty. It's not about multiplying probabilities and utilities. How do we do it? Again, there are two visions. One is, it's a complex problem, we need a complex solution. And here is an example of a typical complex solution. In the marketing literature, it's called the Pareto negative binomial distribution model. I'm not doing mathematics with you, but just look at it and I hope you're impressed. So, what's the alternative? The alternative is, in this case, you study how experienced managers actually do make these decisions, and the result is that you find something totally different. Once again, here's an example, the so-called Hiatus Heuristic. It just looks at one good reason again. So if a customer hasn't bought for 9 months, out, otherwise in. Now, if you think a moment, you would say, but you need to take more in consideration, yeah? How often the person bought, what the spicing is, and so on. Or you might even think that these managers have cognitive limitations, and that's why they can only think with one thing. The true approach is a different one. You test that empirically. How good in this case, the Pareto negative binomial distribution model is compared to that in actual predictions of customer behavior. And here is a study that has looked at 3 businesses, and in the first one, an airline, the Pareto negative binomial distribution model gets 74% correct. The simple heuristic that has only this one variable does better. The same in the apparel and in the CD now. This is a faster turnover business. It's the same. Here at least you save all this effort and thinking and calculation. That is a so-called less is more effect, because the heuristic has only a subset of the information than the more complex model has, and is not only faster, but also more accurate in prediction. It is important that it's prediction. If you do data fitting, then the complex models will always be better. But data fitting is predicting the past. What you already know, that's not. So we have looked at this more closely, whether that could be just an accident, and have looked at 24 other companies and done the same test. And we have also looked at whether this Pareto negative binomial distribution model isn't actually good. So we used logistic regression, and we used one of the big heroes for machine learning, random forests. And I'll show you now on the left side the result. This is an average about over 24 more. You see the Pareto negative binomial distribution model is better than another one from marketing literature. Logistic regression does better, random forest does about as well, and the simple heuristic that just goes with one reason outperforms all of them on average. Then we have looked at other repeat behavior problems, like in healthcare, when a patient is released, the question is, what's the chance that the patient will be back within the next 6 months? So repeat problem. Or whether there's a tornado, what's the chance that another one will be in a certain time? And you see the same result. And I'll just give you that as a hint that there are, in many situations, there are simple solutions out there. You just need to look for them. And it's often a single variable that decides, and all the rest, you can ignore that. One way to understand that is here. So the study of the ecological rationality investigates under what conditions a given heuristic will be successful and where not. And here's a very intuitive condition. Here you have 5 predictors. And these are weights like beta weights. And if the first weight is so big that the sum of all the other weights doesn't exceed the first one, then you just go with this weight, and no other linear model can ever do better. Got this? And there are amazingly many situations where this is the case or approximate the case. What is important is to keep to certain scientific principles. The first one is we need formal models of heuristics. So you may have read the Kahneman-Tversky and now behavioral economics literature about availability, representativeness. These concepts are all informal. You cannot make predictions with that. You can explain almost everything after the fact that's done. And if you formalize them, then you can find out actually less is more effects. And you cannot if you don't be precise. Second, one needs competitive testing, not test your favorite model, like the Pareto negative binomial distribution model, and then claim victory if it's better than chance, but do real competitive. And if you look careful in the economics, behavioral economics literature, you find competitive testing between real different models, like a logistic regression and a heuristic. You find this almost never. It's a kind of confirmation bias research. And finally, it is important to test your model in predicting, not in fitting. In fitting, you always find out that a model with 5 free parameters like prospect theory will win. No surprise. That's a mathematical truism. I add another free parameter, and it will be even better. So we need to do real prediction. Now let me apply that wisdom to big data. That's my last example for you. Remember the showcase of big data? That was when the Google engineers designed an algorithm to predict the spread of the flu and influenza-related diseases. So the idea was that people who have symptoms will enter search terms that in order to find out what they should do or what they have, And so the Google engineers analyzed about 50 million search terms, reduced this to 45, and made a linear algorithm that is secret because it's a business model. And also the weights are secret. We do not know what they are. And then started to make predictions. And this is one of the few cases where the predictions were open available. And as you may have, so the predictions started around 2009. And there was a 4-year calibration where they calibrated the algorithm. Basically, the algorithm learned that flu is high in the winter and low in the summer. And then they make predictions. And remember the swine flu in 2009. It came out of the season. So it started in April and had its high point in September. And the algorithm, of course, could not know that. Any algorithm, whether it is big data or otherwise, as we heard today, only lives from the knowledge from the past. And if the future is not like the past, then that's it. Now, the Google engineers re-engineered the algorithm. What did they do? They operated on the idea, it's a complex problem, we need to make it more complex. And they increased the number of predictors from 45 to 160. If they would have thought in a different way, namely, it's a problem under high uncertainty, there's a virus, there are people involved, then they should have had the insight, we need to make it simpler. But it's the key reflex in our society. Make a complex model. If it doesn't work, make it more complex. It's the same with Basel I, Basel II, Basel III, so in financial regulation, which keep increasing to be more complex. So then I had 160 variables, and you probably know the end. They made for another 4-year predictions, and then they gave up. The problem couldn't solve it. So I want to do a thought experiment with you, and then I show you the realization. Now, if you would apply the kind of thinking that under uncertainty, you need to scale down, you need to make simpler, how would you predict the spread of the flu? Make it more extreme. What heuristic that only uses a single cue, and that's easy available, and you don't need any big data or 50 million search terms, what single cue could predict the spread of the flu? Now, think about the example I had before, recency. Something that happened recent. And the best data that you have in the US is the number of doctor-related flu visits 2 weeks ago. That's the most recent data. So here's a simple heuristic. The number of flu-related doctor visits tomorrow is the same as the one 2 weeks ago. It has a bias, clearly. It can't be right. But it can be more robust than all these complex estimations. And we have tested that on 4 years of Google flu data. So compared the error that the revised big Google flu predictions made, and that's up there. It's a mean absolute error of 0.49%. And the simple heuristic that has no free parameters, just this one thing, has a much lower error. This is an example. Under uncertainty, you may well make better predictions of the future if you simplify it, even extremely, to just one. In the terms that Rory introduced today, and I was really proud about him that he got the point, that was between bias and variance. So this heuristic that has no free parameter may have a bias, but doesn't suffer from variance. So variance is like the sensitivity of whatever you do on different samples. And in many situations, you really don't have large variance. And the complex methods, they both have a problem with bias invariance. And if you have a stable world, then big data will be the better method. But if the world is not stable, then you incur so much variance and overfitting that you can actually predict this kind of results. So this was the short excursion into decision-making under uncertainty. And I was making the point that situations of risk are not the same as situations of uncertainty. In situations of risk, you can calculate the best answer, you can optimize. And these are situations where basically yesterday is like tomorrow. Under uncertainty, an optimal solution in a situation of risk may apply, may not apply. You only can hope. The robust strategies are simple heuristics. This is an application I've not talked really about. Heuristics can also be informative for leadership. So good leaders have a number of heuristics such as first listen, then speak. That for handling people, or also good heuristics for handling strategy. So a simple heuristic is don't buy financial products you don't understand. If that heuristics would have been followed on both sides of the Atlantic before the last financial crisis, the crisis would not have happened this way. These simple heuristics can provide more safety than the Basel III regulations with its immense complex calculations. And finally, methodology. It is very important to follow the principle of science again, to formalize your ideas rather than use vague terms and explain everything after the fact. And also to have competitive tests and don't explain the past, explain the future. And at the end, more information, as you have seen, under uncertainty, more information, more computation, more time is not necessarily better. You can often do better if you find powerful, simple rules. Less can be more. Thank you for your attention.